Motion data is typically represented as a time series of character poses parameterized by joint angles or joint positions. This representation is excellent for data processing, but due to joint angle limits and limits in movement speed, valid human motion only exists in a small subspace of this representation. In this paper we present a method of learning and operating on this subspace, which we call the motion manifold. We train a deep convolutional autoencoder using the full CMU motion capture database. The hidden units of our network parameterize the surface of the motion manifold, and passing data through the network represents projection and inverse projection onto and off of the manifold. After training the network, the filters express strong correspondences. They are also sparse and correspond to local independent features of motion. This allows the network to learn a natural set of bases which represent movements of several joints over a period of time. These components of motion are combined on deeper layers to represent the final bases of the manifold. Having an effective way of encoding a motion manifold has many uses in animation research. Here we demonstrate some of our results. We artificially corrupt motion data by randomly setting values to 0 with a probability of 0.5. Even though half of the information is gone, by projecting the corrupt motion onto the manifold we can recover motion similar to the original. We can also fix motion data from the Connect motion capture system. Joint positions from the Connect can have many errors due to occlusions and systematic error in the algorithm. Here we project the motion from the Connect onto the manifold to recover motion more similar to some ground truth motion captured from an inertia-based motion capture system. We can also account for missing markers. Here we recover motion where the wrist marker is missing. Given some stepped animation data, we can use projection onto the manifold to smoothly fill in the gaps with valid motion. Naively interpolating two very different motions can result in motion that is invalid. Here, a linear interpolation of a push-up motion and a walking motion creates an impossible walk. Using basic manifold learning techniques such as PCA results in almost exactly the same interpolation, but by interpolating along the manifold found by our approach we can ensure the motion remains possible. Using naive Euclidean distance, this confident walking motion is found to be similar to some odd motions, such as a sidestepping motion and an old man's walking motion. Using basic manifold learning techniques such as PCA, the result is not improved. Here PCA returns sidestepping and two old man's walks. But because our network is deep and explicitly encodes time, we can take the min and max over the temporal dimension of the manifold, and then use Euclidean distance to get a distance measure which is temporally invariant and correctly returns only confident walks with turns. In conclusion, learning a motion manifold has many useful applications in animation research, and we believe our approach is powerful, scalable, and easy to use.